This is Relatively Prime, a gerrymandering encore in the mathematical domain. I am Samuel Hansen. This story first appeared as part of the Mathematistan episode in Season 2. It's all about the mathematics of gerrymandering, and I still find it to be one of my favorite stories that I ever produced. I'm particularly re-releasing it right now because mathematics and gerrymandering are very much in the news, and also because I am putting out another episode that features interviews that are all about mathematics and gerrymandering, and I really feel that the information in this show is a great primer so that you can better understand the discussions I have in this new episode that's going to be coming out right after this one. So if you've already heard this and remember it all, that's fine. Go ahead, skip it, don't feel bad. Just go right on to the next episode. But if you want a little bit of a refresher about the mathematics of gerrymandering, give this a listen. It really is a great story. We have one story left, and after some of the heavier stuff that's been on this episode, I really wish that I could tell you that what I have left is heartwarming and soul-lifting. But sadly, I can't do that. I can guarantee that it's a lot more mathy, if that helps. But that being said, we are going to have to start with a political definition.
So gerrymandering is drawing the district boundaries in order to diminish the power of your opponent. So there's different techniques such as splitting and packing. So splitting would be to take your opponent's voters and split them among different districts so that they have less voting power, versus packing is packing them into one or just a few districts. That way they win in those districts, but then they have less power in the other districts.
That was Christy Vaughn. When I spoke with her, she was an undergraduate at Duke, and now she's a graduate student at Princeton studying applied and computational mathematics. And as she made pretty clear in that clip, we're now going to talk gerrymandering. To give us a sense of just how dangerous gerrymandering can be, here's the chair of the math department at Grand Valley State University.
I'm Jonathan Hodge. I'm the chair of the mathematics department at Grand Valley State University.
And when I asked Jonathan about the dangers of gerrymandering, this is the example he gave me. Quick warning here for those of you who are sensitive to political engineering. I personally find this frightening as hell.
We can imagine an example where we've got, say, 4 districts. Let's say we have 100 voters. And let's say there's 60 Democrats, 40 Republicans. Depending on how I draw those districts, I can make the 40 Republicans win 3 of the 4 districts. They've got to have a 13-12 win in those 3 districts, and then they lose by a landslide 24-1 in the remaining district. Or if I just allocate the Democrats and Republicans evenly, or I draw the districts in a way that allocates the 2 parties evenly, the Republicans wouldn't win a single district. You really can manipulate the outcome of an election by the way these districts are drawn.
One of the ways that you do this sort of manipulation, as Christy mentioned earlier, is with a method that's called packing.
There's one in North Carolina that's actually currently the subject of a lawsuit.
That was Jonathan Hodge's colleague at Grand Valley State, mathematics professor David Austin.
It's extremely skinny. It's maybe 120 miles long. It's very narrow everywhere, but in some places it's extremely narrow, like less than a mile wide in a couple of places. And if you look at it, the boundaries are just drawn, and it's just drawn in a crazy sort of way. And it's clear that that's probably an instance of packing, where the district's drawn in such a way that everyone in there comes from a similar background or is inclined to favor one political party, and it's just saying, okay, you can have that district, we'll take the rest.
And the other main method? It's called cracking.
This happened in Columbus, I believe in 2000, when the congressional districts were drawn. Right in downtown Columbus, 3 congressional districts essentially looked like a pie. So that separates out those voters into 3 separate congressional districts and potentially dilutes their influence in an election.
We should probably take a step back here for a second and define some terms. As Christy mentioned, gerrymandering is the drawing of congressional districts for political gains. And actually, we should probably start first with defining congressional districts. A congressional district is a geographical area within a state where the residents vote together to elect a single person to the House of Representatives. And in 35 or so of the states, these districts are drawn by the state legislature, which means that every 10 years when the census comes out and the number of representatives across the states change, the party that's in power gets to draw the new congressional districts. And there's really not many federal regulations governing how these districts get drawn. The only real standard is that the population in each district in a state should be as equal as practical. There is also the Voting Rights Act, which blocks district lines which deny minority voters equal opportunity to, and this is a quote, practice in the political process and elect representatives of their choice. But the Voting Rights Act is quite regularly in the middle of judicial battles, and how it's been enforced has varied quite a lot over the years. To really illustrate just how little regulation there is, only 23 states even require that their congressional districts be connected. That said, almost all congressional districts have been drawn in a connected manner. You may have noticed I keep saying this word, draw. And I don't know about you, but when I'm thinking in mathematical terms and the word draw comes up, my mind goes to geometry. And though I love to think of myself as this totally unique being, I know deep down, I'm really not. So it's no huge surprise that geometry turns out to be one of the big tools which is used when investigating if a district has been gerrymandered.
In particular, you could look at the geometric shape of a district, and you could try to say, does this look like the district was engineered? And usually engineering would require a lot of choice or a lot of human involvement.
Historically, there have been two geometric measures used to try and discern the amount of human involvement. The first looks at compactness. Compactness checks the ratio of the area versus the perimeter of a shape. An example of a highly compact shape would be a circle. It has a very high ratio of area to perimeter. For a shape with low compactness, think of a snowflake. There's a lot of perimeter, but not much internal area, so the ratio of area to perimeter would be really low. And so a district with low compactness that has a lot of perimeter, but not much area, it would, at least at first perusal, seem more likely to be an engineered shape. That is at least in part because one of the things that compactness checks for is how strange a shape is. Just by checking for districts with low compactness, we can find the shapes with strange-looking zigzagging boundaries. And while this alone does not indicate anything untoward, it is a starting point. The other starting point is checking a district's convexity. A shape is convex if you can draw a straight line between any 2 points in that shape, and the line never leaves the shape. So a circle is convex, but a circle with a pie piece taken out, think Pac-Man here. That is not convex. Since if you draw a straight line from Pac-Man's eye to, say, the bottom of his mouth, that line would have to go outside of Pac-Man. There's a lot of different tests which use these two ideas, compactness and convexity, to try and determine the likelihood that a district has been gerrymandered. Jonathan Hodge helped develop one called the Convexity Coefficient.
So what the convexity coefficient measures is the probability that between two randomly selected points in the district, you will stay within the district if you draw a line between those 2 points.
It turns out convexity is not one of the easiest things to measure. But with some help from computer simulations, Jonathan and his colleagues computed convexity coefficients for districts across the United States. What did you find a higher coefficient versus lower coefficient? What did the actual simulation show?
Well, Wyoming's pretty high because it's a rectangle with one congressional district. So
that would do.
Yeah, Wyoming has a convexity coefficient of 1. On the other hand, if you look at average convexity coefficients in places like Maryland, you get fairly low coefficients. A lot of that, though, is due to the fact that the boundary of the state itself is very non-convex.
That brings up an interesting point. Some states, especially those near the East Coast, have very strange borders like West Virginia, or exceedingly odd coastlines like Maryland. And these odd state boundaries can definitely bias compactness and convexity tests. And for people looking at gerrymandering, it turns out that they have to worry about more than just state boundaries. The population distributions in a state could also throw a spanner in the works.
If I tweak the boundary of a district in a very low populated area, that's not going to have really much effect on the outcome of an election. On the other hand, if I make a small tweak in a highly populated district, that could make a big impact.
Jonathan and his colleagues were quite aware of these problems while they were working on the convexity coefficient. And after accounting for them, Maryland did actually start to look better. But not all states fared so well.
Other states, like North Carolina, things actually get worse if you adjust for the population and the boundary. That ignoring the state boundary and ignoring population, you actually get a better convexity coefficient, which suggests that the lack of convexity within the congressional districts in North Carolina, for example, is not just due to irregularities in the state boundary or the way the population happens to be distributed. It suggests that there's evidence of gerrymandering going on.
Keep North Carolina and this potential evidence of gerrymandering in your head. We're going to be coming back to it. But before we do, let's talk about another gerrymandering test, this time with David. Once again, this test takes into account state boundaries and population distributions. But I will say, it has a way more fun name than convexity coefficient.
So what you do in this case is you choose two random people in the congressional district, and you look at the length of two paths joining them. So the first path that you look at is the shortest path between them that does not leave the district. The second path is the shortest path between them that does not leave the state. So you look at the ratio, and you take the average of those over all the people in the state. That average is called the bizarreness.
Bizarreness was developed? Actually, just a second. I really want to soak in how great it is that a test for gerrymandering is called bizarreness. Okay, I'm done. Bizarreness was developed by Chambers and Miller. And similarly to the convexity coefficient, the test found that really odd-looking Maryland district, the highly non-convex and non-compact district, to not be very bizarre. It actually scored really close to 1, which is the least possible bizarreness score. So we have this district, which in isolation certainly looks gerrymandered to my eyes, but two different tests indicate that it probably wasn't. Should I take the test's word for it? If a test says that a district isn't gerrymandered, is that the last word? What if a test shows the opposite, that it's highly likely that a district is the result of gerrymandering? Is that proof enough?
In terms of drawing some sort of objective standard, you take any measure of shape compactness, you say, well, above a certain point, there's gerrymandering, below a certain point, there's not. That's really not a good way of doing things because any sort of benchmark you set there is going to be arbitrary. I think these sorts of measures of shape compactness allow us to identify potentially gerrymandered districts.
There's not a single measurement. These measures all have different qualities and emphasize different features of a district. So rather than looking at a single measure, probably the most appropriate thing to do is to look at a variety.
Well, that wasn't very satisfying. At least they agree. I guess that's good. It's too bad that these geometric measures can't tell us for sure that a district has been gerrymandered. It is probably more believable than if they said they could, though. We all know the real world is not as cut and dry as the mathematical one. It does beg the question of what if we went beyond just geometry? Could our solution lie in that direction? Well, the answer is... Oh, come on. You didn't really think I'd tell you the answer that easily. You know me better than that. Instead, I want you to remember back to when I told you to keep North Carolina and possible evidence of gerrymandering in your mind. Because we're going back to Christy Vaughn and her professor,
Jonathan Mattingly, professor of mathematics at Duke University.
And work that they did to try and determine if the districts used in North Carolina's 2012 election had been drawn fairly.
Different than what a lot of people do, it wasn't about trying to come up with new districts or trying to decide how compact or the properties. And we were really just trying to answer the question, how representative were the current districts? The fact that got it all started was that in 2012, in the congressional elections, the majority of North Carolinians voted for a Democrat, but yet only 4 out of 13 were elected.
As he said, they didn't focus on convexity. They didn't focus on compactness. They simply focused on how likely the 2012 election result was. This means their approach was very different from anything that we've talked about so far.
Let's randomly choose new redistrictings and then rerun the 2012 elections exactly as they happened. That is to say, each voting precinct votes in the same way it did in the actual election. And all we change is which voting precincts are in which congressional district. And we would randomly draw these.
And now, if I know you as well as I think that I do, you want to know what they found. Don't worry. I did too.
No matter how you drew the district boundaries, we saw more Democrats elected under our randomly chosen district boundaries. So even though there were 4 elected back in 2012, our randomly chosen districtings had 6, 7, or 8 Democrats elected.
With 7 being the most likely.
Did you have any cases where you actually had 4?
Never.
Never.
That does show a problem.
Yeah.
Just as before, this test is also not perfect. It requires the assumption that people are going to vote for the same party no matter which district they're in and which representative that means that they're voting for. But while they both stress that people vote for individuals, not for parties, Christy and Professor Vaughn also pointed out that in our increasingly polarized political climate, it's probably not that bad of a proxy. He in particular had a rather heartfelt and strong opinion as to what these results mean.
We like to talk about the results of the election. And this really shows that, that's not so hard set, right? I mean, you took the exact same votes in the exact same precincts and just changed which congressional district the precincts were in. And all of a sudden, we get completely different results.
While this result is super interesting, and they do think its implications are quite strong,
it was so unlikely in our model that you would ever end up with 4, that if you had a system that gave 4, you have to assume that it was designed to do so.
I once again couldn't get anyone to say that this proves for sure that the state has gerrymandered districts.
We'd like it to be a warning bell, some way of measuring what's really beyond the pale, what's really an unacceptable redistricting.
There's this one thing that I asked all my guests. Is there some sort of algorithmic way that we can solve gerrymandering? Could we just put a computer on district drawing duty and be done with all this? Well, they said no. To go a bit deeper, here's what David Austin told me.
If you come up with an algorithm, with a little bit of work, you can usually come up with population distributions that would break that algorithm or lead to districting that just doesn't seem fair.
This again comes back to us not really having a perfect objective measure to work with. We've seen that compactness alone, convexity alone, and even combinations of the two not quite cut it. And even when I decided to take this idea of the will of the people not being a single outcome, but a distribution of outcomes, very, very literally, there was still a problem that I probably should have thought of. So now I know that this is in no way what your research is, but this just popped into my head, so I'm going to suggest this as a possible political fix here. Do you have any feeling that maybe we should let people vote as they would vote and then do exactly what you did in order to decide the best way?
I mean, that would work more in a parliamentary system, right?
Yes.
Where you're voting for a party. Where you're really voting for a party. I think in our current system, that's not really tenable.
So what's the fix here? Personally, I don't know. I guess the nonpartisan committees that some states are now using to draw district lines are a good start, but to be fair, I'm not sure about them. I hope that some of the people that I talk to for this take a look into the districts that they've come up with soon, just so that we have a better idea. I don't like to say it because I hate to admit this about any problem, but it doesn't look like mathematics can solve gerrymandering for us. Not that it has no role to play. We still need to be able to identify these potential problem districts somehow. Gerrymandering, it's this super scary problem. It took us centuries to just get to the point where everyone finally had the right to vote. And now, thanks to gerrymandering, all of those votes, they aren't even worth the same amount. And that's just not right. A point that Jonathan Mattingly made very strongly.
Just making sure that each person gets to vote is not sufficient to safeguard the democracy.
If you don't want to take a mathematician's word on this, I totally get it. This is politics, not mathematics. And I don't listen to politicians when they tell me their opinions on the Riemann hypothesis. So instead, let's hear some words from a politician.
There's a really good quote in Barack Obama's book, The Audacity of Hope. He says, "These days, almost every congressional district is drawn by the ruling party with computer-driven precision to ensure that a clear majority of Democrats or Republicans reside within its borders. Indeed, it's not a stretch to say that most voters no longer choose their representatives. Instead, representatives choose their voters."
And there's really nothing that I have to add to that. But before I let you go, as a matter of journalistic due diligence, I asked all of my guests if they thought that the mathematical study of gerrymandering was driven by partisan goals. They said that it wasn't. And in Christy's case, it turns out that I was not the first person to ask her.
One commenter was saying, "Oh, why didn't you do this back when the Democrats were in control?" And my response to that is that I wasn't an undergrad back then. So I'm undergrad now, so.
Actually, she's a graduate student now. And all you gerrymandered districts, well, you better beware. Because what that means is that she has even more mathematical tools with which to find you. And you better believe, I want her to find you all. That is all the time we have for this Encore episode of Relatively Prime. And I'm going to keep these credits short. I'd like to thank Jonathan Hodge, David Austin, Christy Vaughn, and Jonathan Mattingly for appearing on the original show, Mathematistan, from Season 2 of Relatively Prime. And if you'd like to know more about them, head on over to relprime.com and check out the show notes for this episode or for the Mathematistan episode. I'd also like to thank Lowercase N for the music. Find them on Bandcamp. Relatively Prime is a Patreon-supported show, and if you'd like to back it, head on over to patreon.com/relprime. It's also licensed with the Creative Commons Attribution Share-alike license, so please feel free to remix it as long as you say where it came from. And that's all. Thank you for listening, and make sure to check out the other episode right after this. It's amazing. Go listen to more mathematics and gerrymandering. Have a matherific week, y'all.